This is example 13.5 from Discovering Design with Chemistry. A 125 gram ice cube is at a temperature of negative 8.7 degrees Celsius. At 1 atm, how much energy would it take to turn all the water in that ice cube to vapor? And then they give us the C for ice, the specific heat capacity for ice. They give us the latent heat of fusion and the latent heat of vaporization, freezing, and the latent heat of vaporization, so that we have all the kind of default numbers that we need. So before we start, let's kind of draw a picture of what's happening here. So we have an ice cube, and our cube is at negative 8.7 degrees Celsius. If it's going to turn everything in that to vapor, it has to first turn into a liquid. But to turn into a liquid, we've got to heat it up enough so it's at the melting point, which is going to be 0 degrees Celsius. And then it has to have a phase change so that it turns into just liquid at that. It's still at 0 degrees Celsius, but just liquid. And then finally, it has to reach the temperature at which it would like vaporize or become water vapor. So we've got to get it up to still water. We got to get it up to 100 degrees Celsius, the boiling point. And then at that point, the water, still at 100 degrees Celsius, can have a phase change and turn into gas. How am I going to draw gas? I'll just draw what looks like steam coming up, even though we know that steam is not really water vapor. It's actually condensed droplets of water on dust in the air, but whatever. Close enough. Okay. Call it vapor. Didn't think through my picture before I got started. Okay, so we're going to have to do multiple steps to get that answer. So the first step is a temperature change. That means we need to go back to the thing that we've already done, the Q with the temperature change in it. So let's label what we know. We have the mass of the ice cube. We have the initial temperature of the ice. And the 1 atm is just helpful information to know that we don't have to do anything weird, but we're going to actually ignore that because we're not dealing with pressure right now. And then we have the C for the ice cube. So we have M, initial temp, and C. To do this problem, we need a final temp so we can subtract and find the change in temperature. Thankfully, we know the final temperature of the ice. That's going to be the 0 degrees that we're aiming for. And so let's start with change in temperature so that we can get that set up. So final minus initial. So 0 degrees Celsius minus negative 8.7 degrees Celsius. And I put in parentheses so we didn't accidentally drop that negative when we subtracted. So we're going to plus. So the temperature change is 8.7 degrees Celsius. We don't have to worry about the significant figures because 0 degrees Celsius is considered an exact number. So there's our temperature change. So now we can find the Q of just going to 0. How do I want to say that? Let's say Q, I'm just going to call it Q1 because that's our first step. So step 1. All right, so M, C, change in T. 125.0 grams. Our C they gave us, remember our specific heat capacity is different for different things. We know what it is for water, but they've given us what it is for ice. And then our change in temperature. Oops. All right, so we're going to put all these together. We are only going to be able to have 2 significant figures in our answer because of that 8.7. So just make note of that. So 125 times 2.093 times 8.7. All right, so we only get to keep 2 of those significant digits. That means the first 2 numbers. So we're going to round up to the hundreds place. So that's going to be 2300, and that's joules because our units here and here cancel, leaving us with just our joules. All right, so that's our first Q. I'm going to move this a little bit to the side because I'm going to box them until we get to the last answer so we can keep track of our things. All right, so that was step 1. Let's change color. So now we're going to go, actually let's do blue. Yeah. Now we're going to go this one. This is going to be our step 2. We're not actually changing temperature here. We're just changing phase from the solid ice to the, or the solid water, I guess you can say, to the liquid water. So this is where we're going to use our newest formula that we've recently learned, where our Q is just mass times that latent temperature. So our mass is still 125. We haven't changed mass because that doesn't change. And then we're going from frozen to liquid. So since a frozen is involved, we need the L of F. So, or LF, however you want to read that. Joules per gram. All right, our grams cancel. And this time we get to keep 3 significant digits. And so we're going to multiply that, and then 125 times 334. All right, so we're going to keep 4, 1, and round the 7 up to 8. So 41800. All right, so there's our second one. We're going to call that Q2. So that's the energy needed to get from one thing to the next. So we've got 2 pieces of our energy. All right, let's go to the third piece. All right, so now we have our third step. We're going from 0 degrees to 100 degrees. We're back to changing temperatures. So because we're changing temperatures, we want the one that has the change in temperature. I'm going to squeeze it up a little so I don't lose my picture or my problem, but I have more room. So again, we're back at MCAT. I know that that triangle is not an 8, but it helps me remember the formula. So 125.0 grams. Now this time we have water involved, so we know what that specific heat capacity is, or we hope we do because it should be memorized. And then we're using our change in temperature. So I know it's increasing by 100, so I can just put in 100, but I can also, if we wanted to come to the side and calculate the change in temperature for this one, final minus initial equals 100 degrees Celsius. And those are exact because those come from definitions. So this 100 that we're going to use here does not affect the, we don't account for it when we're counting for significant figures. This one will matter, and this one in fact also matters. So we have to limit it to 4 significant figures for this particular one. All right, so let's multiply those out. So 125 times 4.184 times 100. All right, so in this case, we have, if we want 4 significant figures, we need that 0 to count, but the other 0 not to count. So what we're going to do is we're going to use scientific notation to mark this. We're going to write 5230 with our decimal right after the 5, which means our decimal point has to move from 1, 2, 3, 4 places over. So we're going to put 5.230, so we have 4 significant digits. Oh, no, not 4. Can't keep my calculator up in this at the same time. That's a shame because I have a bad memory. Times 10 to the, and we moved 4 places over. That's where the 4 came from. So pulling it back up just to check it. So 5230, those are the numbers I want to keep as significant. The decimal goes between the 5 and the 2, which means I moved it 4 places over. Okay, so that is our Q for step 3. All right, so now we have one more final step to finish off this question about stuff, and that's our last step here. Oops, the arrow line up better. This is step 4. We're not changing temperature, we're just changing phases, which means we care about latent heat. So it goes down here. I put a little note down here in the bottom to help us remember that latent heat means the heat for a phase change. It does not mean any temperature changes happening. So every time we're changing phases, but we're still stuck at that 0 degrees or that 100 degrees or whatever temperature that substance changes phases at, the latent heat and the mass go together to find that Q that you need, the energy, and not, it doesn't involve anything having to do with any changing temperatures. All right, so let's get our last one. So Q, this one is, it looks like milliliters. I'm going to put a dot in there. Okay. So again, we have our mass, same mass, because we didn't take away any of the mass, we're just changing phases. This time we're going from a liquid to water vapor. We're wanting to vaporize, so we're going to use the L with the V in it. So 2260 joules per grams. And our grams get canceled out. So the 125 have 4 significant digits, and the other one is not, yeah, that's not gonna, it's only gonna give us 3, so we're gonna have to limit it. Okay, here we go. 125 times 2260. Okay, so we got to limit it to 3 significant digits, so we're going to have to round it to just these 3 places. So that'll be 283,000. We do keep the other zeros. I just realized I didn't put a J in my green one there for step 4. See if I can squeeze one in. J. There we go. Okay, you have to have units. All right, so now what we have is we have the energy that it took to go through the temperature change, the phase change, another temperature change, and then a final phase change. To get the energy that it needs to go from water at that temperature all the way up to water vapor, we need to add all those energies together. All right, so let's slide this over or up. Yeah, let's go up. All right, so let's take, what color haven't I used yet? I'll use that one. All right, so I have 2300 joules plus, I just realized I probably should do this in all their matching colors. No, that would take too much time. Just kidding, I'm not doing that. 5. For this one, just temporarily, I'm going to write 5.230 times 10 to the 4th, but underneath I'm going to write what that number was, 5230. 1, 2, 3, 4, so that I can remember what it was, because for adding that'll make it easier. Because when I type in the calculator, I just don't really feel like adding in a scientific notation one in the middle of all those other totally normal looking numbers. All right, let's see if I can do this without looking at all my numbers. Plus 0 plus 52300 plus 28300. All right, so before we write this down, we're adding things, and so these all have to have, it's underlined. So this one is the hundreds place, this one is the hundreds place, this one is this 0, which is the tens place, and this one is the thousands place. Because we're adding, we care about place value, not the number of significant digits, and we need to go with the least precise. So between tens, hundreds, and thousands, which are our 3 different options, thousands is the least precise, so that's what we have to round it to, is the thousands place. So looking at this number, that means we have to round it to that 9 right there. So it's going to be 379,000 and just zeros after that. So 379, that's where our significant digits stop, and the rest are zeros. All right, so that's our final answer. That is how much energy it takes to turn water an ice cube at -8.7 degrees Celsius all the way to water vapor.